Hello and welcome to 8.1 Solving Systems of Equations Graphically. Basically, we're going to take a quick look at what systems of equations are, and then what does it mean to solve them, what do our solutions mean, and figure out how to do that. We'll be taking a look both at Desmos as well as with your graphing calculators. Most of you have the TI-83 or 84 models, so we'll be using the TI-84, very similar technique for either one of those. Let's get started then. So first things first, the system of equation is a collection of two or more equations that use the same variables. Usually we're going to use x and y as our variables. And then our solution to a system of equations is a point that satisfies every equation in the system. So right here we have our first graph we'll take a look at. We have two lines, two equations in that graph, and where they meet, that is our solution. That's the point, so in this case negative 2, 1, that satisfies both of these equations. Let's take a quick look at these lines here. So this blue one, we see our y-intercept at 3, and we see we're going up 1 and over 1, so we have a slope of 1. Okay, so we know that our equation then is y equals x plus 3. Again, in front of the x, we could have that 1 for our slope, rise over run, and then our 3 being our y-intercept. Okay, then for the green line there, we see our y-intercept is at 0, and we see that our line is going down 1 and over 2. Okay, so that's going to give us y equals a slope of 1/2, again, rise over run, and we don't have our y-intercept is 0 there. Okay, we notice also that this line, this green one, is going down to the right, so we have to add in that negative for our 1/2 x. Okay, so then we could say then for the system of equations, y equals x plus 3 and y equals negative 1/2 x, our solution is negative 2, 1. Again, that's where our two equations meet. Okay, so we have a few different options here when we're taking a look at this. First of all, we have our linear quadratic systems of equations. So we're going to have one linear equation and one quadratic. Okay, so we'll have a line and we'll have a parabola. We also are going to see quadratic systems of equations. And again, that means we're going to have two parabolas. All right, so what can happen here? We can have no intersection. Okay, so in this case here we have in this case here are two equations. So in this case here, the lines created by our two equations do not meet, therefore we have no intersection, and therefore we have no solution. Okay, sometimes we will have one solution. In this case here, we see we meet at one point but no other ones, therefore we have one intersection, thus one solution. Lastly, we can have two intersections and two solutions. So here we see we have our two intersections and two solutions. Same thing goes for our quadratic systems of equations. The number of intersections we have is equal to the number of solutions we have. So let's go ahead and put this into practice then. We have our system of equations made up of our y equals x squared plus 5x minus 6 and y equals negative 2x minus 1. So whenever we see these questions, the first thing we're going to want to do is get them into y equals format. We can see this one's already done for us, so that's great. So let's go ahead and try to graph this one. Eventually we will just plug it into our calculator to graph them, but it's good to make sure we always remember how to graph these on our own. Okay, so let's start by finding the roots of our first equation. So first of all, we know we're going to have our x and our x in the front. Again, we're multiplying those to get our x squared. Next, we want to figure out, okay, what's going to multiply to give me -6 and add to give me +5. Well, we're going to have a +6 and a -1. Okay, so this tells us that x equals -6 and x equals +1 are my roots. So I can go ahead and graph those here at x equals 6 and 1, 2, 3, 4, 5, 6. Okay, always good to label our axes. Okay, next we want to find what the midpoint of our parabola is. Okay, as soon as we see that x squared, we know it's a parabola. So we want to find what is the midpoint, also what is our x coordinate of our vertex. So we can do that by finding the midway point between our -6 and our 1. So if we take -6 plus 1 divided by 2, we're going to get -5/2, or -2.5. Okay, we can plot that as well. So if I go -2.5, I know I'm going to be on that line. Now it's good to know what our y-coordinate of our vertex will be. So let's go ahead and find that out. Again, for that, we just sub in this -2.5 into our original equation. Okay, and this works out to -12.25. Unfortunately, we're going to be graphing a little bit off of our Cartesian plane. That's all right, though. We'll go ahead and label that. So again, we had an x-coordinate of -2.5 and a y-coordinate of -12.25. So we can go ahead and draw a parabola in there. Again, looking something like this. Should be nicely curved if we're drawing it accurately. Now let's go ahead and graph our other line. That one, fair bit easier. So we know we have -2x minus 1, -1 being our y-intercept, -2 being our slope. Again, that's going down 2 and over 1, down 2 over 1, down 2 over 1. And we can draw in that line there. This one should be straight. Okay, so then again, we had talked earlier about our solutions being where our points intersect. Okay, so then we can see that our intersection points there and there are going to be our solutions. All right, so from graphing this here, we see it's a pretty rough sketch and it's difficult to tell what our actual solutions are. This is where our graphing calculator can come in handy. So let's go ahead and take a look at how we would find what these solutions are when we can't find exactly based on the graphs we drew. All right, so we've switched over to our Desmos app here, which you guys all have. I've already typed in our x squared plus 5x minus 6 and our -2x minus 1. Really nice thing about Desmos. So now to find my intersection points, all I have to do is click on those points. We can see that we have 0.653, -2.307 as one intersection point. And if I click on the other one, we have -7.653 and 14.307. So those then are our solutions for our graph. Again, this means for our system of equations with these two equations, the 2 points that satisfy both equations. Again, these are the only 2 points in our whole Cartesian plane that satisfy these. So these 2 points being then, if we round, 0.7, -2.3, and the other point, -7.7 and 14.3. Okay, so let's go ahead, hop back to our notes and finish up. So we'd want to say that we have solutions at -7.65 and 14.31 and 0.65, -2.3. 3, 1. All right, let's carry on. All right, so as you can see here, we're asked to graph each system and determine the number of solutions. We don't actually have to work too much out here. We just want to figure out how many solutions we have. So why don't you go ahead and pause this video while you graph these 6 equations, and then hit play and we'll carry on. Awesome, so hopefully you got the same as I did for these graphs, again considering our what values in our equations are our y-intercepts, what are our slope. But we end up seeing we have one solution here, no solutions in that second one, and both equations create lines on top of each other for this last one, meaning we have infinite solutions. So what we see then is that if we have a different slope, we're going to end up always having one intersection point. If we have the same slope, in this case both having a slope of 1, we're going to end up with parallel lines, and we notice that we have different y-intercepts, thus our parallel lines are not going to be on top of each other, meaning they will never cross. Lastly, we have our infinite solutions. Here we have what looks like a different slope, but in this second equation, if we divide everything by 2, we end up with y equals x plus 3, which works out to be the same equation that we had in the first place. So if our whole equation is just a multiple of another one in our system, we're going to end up with parallel lines of the same y-intersection point, meaning they're one on top of the other, and again, infinite solutions.